All right, here's your last multiple choice review for the most missed questions. This is for review number 8 on AP Classroom. And I'll just walk through your last ones here for you. Here's our first one. The chemical equation represents the equilibrium that exists in a saturated solution of silver carbonate. S represents the molar solubility of silver carbonate. And which of the following mathematical expressions shows how to calculate molar solubility? Well, the first thing you should be thinking about here is I want to set up a little ice box for this problem. We don't care about the solid. There has to be enough of it to reach the saturated solution that it says in the problem. All we care about is the concentration of our ions at equilibrium. And S is our molar solubility is how many moles of the compound can dissolve per liter. And if you set up an ice box, I'll show you where your S value comes in. So our ice box, the solid, we don't care about. There has to be enough of it to reach equilibrium. And then we start out with none of each of our ions. Our change, we would add 2x and x to reach equilibrium here. And then that would give us equilibrium concentrations of 2x and x. While our KSP expression would be 2x squared because we have 2 of our silver ions times x for our carbonate ion. And this x value is your molar solubility. If our x value was 1, that would mean we would have 1 mole of this that could dissolve per liter of solution. And we'd end up with 2 moles of silver and 1 mole of carbonate. But the actual x value is our S, our molar solubility. So I'm replacing x with S here, and then we just have to solve this for S, and you get this. S equals the cube root of the KSP over 4. And so I hope that helps for that problem. Here's our next one, another KSP expression. This one tells you have 1 liter of solution that has silver nitrate and lead nitrate already in it. It gives you a concentration of your silver ions, and it gives you a concentration of your lead ions. And then it says we add a certain number of moles of a sulfate to the solution. What do we want to know if we're going to be able to predict if a precipitation reaction will occur? That's what's asking, is if a precipitation reaction will occur. I don't have that answer choices here, but each choice reference precipitation. So we want to know, do we have a high enough concentration of silver and sulfate ions to create an oversaturated solution? In that case, we would have a precipitate form for either one of these. So my silver ions are given to me, my lead ions are given me, but we need to figure out what's the concentration of sulfate ions in this 1 liter solution. Well, it tells us how many moles are dissolved in it, and it's in 1 liter. And so we can calculate our molarity of that just by taking our moles divided by liters, and we get 0.0010 molarity. Now, from that molarity, we want to calculate to see if we're beyond our saturation point. So you want to set up a little ice box or an equilibrium situation for each one of these compounds, the silver sulfate and the lead sulfate. And so our first one would be silver sulfate breaks up into 2 silver ions and 1 sulfate ion. The KSP would be our silver squared times our sulfate ion to the first power. And then we just take our concentrations that we calculated earlier, plug them in. We call that a Q value, reaction quotient, because we don't know if we're at equilibrium or not. And that comes out to 4 times 10 to the negative 7th. If you compare that to the KSP given to you in your problem, the KSP for silver sulfate was 1 times 10 to the negative 5th. Our Q value is less than our KSP, and that means that the concentration of silver and sulfate are low enough that we haven't reached a saturated solution yet. So we won't have any precipitate form from this particular setup for this particular compound. But for our other compound, if we plug in our values, we're going to do the same thing. We're going to have a concentration of each times each other. If you plug in those, you get 1 times 10 to the negative 6. Well, 1 times 10 to the negative 6 is larger than 1 times 10 to the negative 8, which is the KSP given to us in our problem for our lead sulfate. And since this is a smaller value, we're going to have a precipitate form. In other words, there's too high of a concentration of lead and too high of a concentration of sulfate in the solution. So to reach equilibrium, the reaction is going to shift to the left, and it's going to produce some solid. And that's what we mean by having a precipitate form. So that's how you compare your precipitate reactions. Our next problem, the reaction system represented above is at equilibrium. Which of the following will decrease the amount of calcium oxide in the system? Well, I'm going to go through these one by one here, just so you can see what would happen for your shifts. So if we want to decrease the amount of calcium oxide in the system, we want a shift to the left. And to get a shift to the left, there's a handful of ways that we can do that, but let's just evaluate the ones that are given to us. A, increase the volume of the reaction vessel at constant temperature. what would an increase in volume do? Well, an increase in volume would take, for a K reaction, or a K expression, it'd just be the concentration of CO2. That's the only thing that would appear in this. But the other two are solids. And so if we increase the volume, what happens to the concentration of a gas? Well, it spreads that gas out. And so if you increase the volume, it decreases your concentration. So we would have a Q value then at a lower concentration. Maybe we double the volume, that'd be half the concentration. And so the Q value would be 1/2 of our original K value. And so Q would be less than K. It would look like this on a number line, which means we'd have to shift this direction to reestablish equilibrium. And that would not decrease the amount of calcium oxide, that would increase it. So this is not the correct answer, go the wrong direction. Lowering the temperature of the system. If we lower the temperature of the system, we want to consider our delta H value. It's a positive value, so that means heat's on this side. So heat would be a reactant. If we lower the temperature, you can picture that just like a reactant. And if we remove heat, we're going to shift to the left to reestablish equilibrium to try to replace that heat that was removed. And if we shift to the left, that would decrease the amount of calcium oxide. So this is the correct answer. Let's evaluate our other ones. C, removing some CO2. If we remove CO2, it'd be the same effect that we described here by doubling the volume. Removing CO2 would decrease your concentration of CO2, and we'd have a Q less than K. So that's not correct. And then D, remove some calcium carbonate. If we remove calcium carbonate and it's already at equilibrium, it won't do anything. The amount of solid doesn't matter as long as we have enough to establish equilibrium, but once equilibrium is established, you can remove all the solid from this container and it wouldn't change the amount of CO2 gas. And so that's how B is your correct answer. Our next one, the equilibrium reaction between chlorine, Cl2, and H2O at 25 degrees is represented above. If a solution at equilibrium is diluted with distilled water to twice its original volume, which of the following gives a value of QC? If we have, we're already at equilibrium. If we double the volume, we're going to take the concentration and divide it by 2. And you can think about it like this. If there's twice as much H2O, there's twice as much space for each of these ions to be spread out, and that would decrease your concentration by 1/2. So my Q value is going to be my Kc value, but on top I'll have 1/2 of the original concentration of H3O plus. And I would also have 1/2 the original concentration of Cl minus, and I would have another factor of 1/2 for the concentration of HOCl, divided by 1/2 of the concentration of Cl2. So let's look and see what happens here. The 1/2s, one of these 1/2s cancel. This one cancels with this one. And we end up with 1/2 times 1/2 on top, which is 1/4. So we would get 1/4 of our original concentrations, which would be this expression right here, if you take those 1/2s out. And so it'd be 1/4 of our Kc. And let's see if that's one of our choices here. There it is, D is our correct answer. QC would be Kc over 4. And then it has a little statement here. The rate of the forward reaction will be greater than the rate of the reverse reaction. The other one says the reverse of that. So how do we know that? Well, if we're 1/4 of Kc and we put it on a number line, Q has to be less than Kc. We have to shift right to reestablish equilibrium. And if we shift right, that means our forward rate has to be larger than our reverse rate at this point in time when our Q is 1/4 of our K value. So that's how D is your correct answer. The forward rate would be greater. Our next one, which of the following changes alone would cause a decrease in the value of K for the reaction? I'll walk through these one by one again here. For changing K, you can't change K with anything except for your temperature. Those are the only things you're looking at for changing a K value. We looked at earlier how changing the concentration would change not the K value, but the Q value. And that's true, but this number would remain constant the whole time through this problem. The same thing for a problem over here where we changed our K or our Q value, but the K would remain constant the whole time. So whatever this number was for K would remain constant unless the temperature changes. So here, we're only looking at temperature change, which the following would cause a decrease in value KEQ. Let's look at decreasing temperature. Delta H is less than 0, so we'd have plus heat on the product side. And that means if we decrease the temperature, we'd remove heat from the scenario, and this reaction would want to replace that, and it'd shift to the right. What would that do to A? Well, K equals products over reactants. And if we shift to the right to reestablish equilibrium, that means our K value, we're going to have more product and less reactant, is going to increase. So we'd increase our K. We don't want to increase K, we want to decrease it. So if you increase the temperature, we're going to add heat to the chemical reaction, and it's going to shift away from what we added. That's Le Chatelier's principle. The reason it shifts away is because our K value changes. At new temperature, we have a K value where products over reactants decreases. And the reason it decreases is because we're producing more reactant as we add heat, and more reactant would be a larger denominator and less product, a smaller numerator. And if you have a larger denominator and smaller numerator, your K value gets smaller, it decreases. So that's why B is correct. These last ones don't change the temperature. Adding a catalyst doesn't do anything for your K value. It just makes us reach equilibrium sooner. Increasing or decreasing volume will change your Q value, but not your K value. So these are not correct either. Okay, this particular problem gives you 3 reactions. It wants you to use the first 2 reactions to calculate the K value for the third reaction. And if you don't remember how that works, this is very similar to Hess's law in thermochemistry, but we're doing kinetics. And so if you take 2 reactions and you add them together to get a new reaction, you'd multiply the K values. So we need to figure out what do we do to reaction 1 and reaction 2 so that they add up to get reaction 3. Well, let's find our CH4. It's right here. This particular reaction we'd have to flip over. And our CO2, let's find that. Here it is. We want it on the product side when we add these together. So this one would have to flip over as well. And then would that take care of our H2? Well, we'd have 3 H2s here and 1 here. So a total of 4 H2s, but both these would be flipped. So they'd be on the product side. So our 4 H2s would work out. Our 2 H2Os, well, here's one of them. It'd end up on the reactant side. Here's the other one. It'd end up on the reactant side. So that would work out as well. And then the COs, carbon monoxide, would cancel. So now if we flip both these, they're going to add up to reaction number 3. What happens to our K when we flip it? Well, remember, this is originally products over reactants. If I flip the reaction, it just flips these over. Now my reactants became products and my products became reactants. So it'd be K, but the reciprocal of K1. And then this one would also be the reciprocal of K2. And so now these reactions would add up to my overall reaction for reaction 3. And their K values would be 1 over K1 and 1 over K2. And if they add up together, I'd multiply them. So I get 1 over K1 times 1 over K2. Let's see if that's one of our choices down here. There it is, D. You just multiply those together, and that's a correct answer. And that's it for this particular review. I hope that helps, and I hope you're feeling prepared for your AP test. Good luck on your AP test this week, and good luck on any other tests that you have as well.